I'm a chemical and a material scientist. My interests are focused on the unique physics and chemistry of functional materials and their promising applications in sustainability. Today, I'm going to talk and share something about the optimization of MEER and its manufacturing processes for our global scale climate control project.
Xiaowei, if you could speak just a bit louder, I think that would help with the presentation.
Okay, sure. So can you hear me clearly?
Yes, that's better.
Okay. So the goal for us is to find optimal materials and develop scalable manufacturing processes for our global scale climate control infrastructure. So eco-friendliness and durability are central for our efforts. In this talk, I'd like to discuss how we make material choices. And we will also share our current plan for realizing the required MEER topology. Okay, let's move to the first part. The starting point for any engineering project is to list the technical and scale requirements. First, the MEER must reflect the sunlight with a high reflectance greater than 19%. Stability in the field is also important, especially in a corrosive, high solid environment like the ocean. Here we target MEER devices with at least 30 years lifespan. So considering the scale of the problem, we must be able to produce each 1 meter squared of MEER at single-digit dollar cost levels. So this also will help us, our approach become financial advantageous with respect to other schemes for thermal offset. Besides cost, there must also be enough materials on Earth to enable manufacturing at the scale we needed. Therefore, we have focused on design on using only the most abundant of elements on Earth. These include the oxygen, aluminum, silicon, sodium, and calcium. Hello, can you hear me?
We can hear you now, yes.
Yeah.
Go ahead.
Okay. So these elements include oxygen, aluminum, silicon, sodium, and calcium. We can also use small amounts of some other elements, including the carbon, iron, and titanium. More specifically, there are two options. One is first layer coating type. This MEER topography has the reflective substance on the top of the support structure materials with no additional protective paint. The other option is backside MEER, which usually has a protective paint on the reflector film to reduce current. So which type is more suitable for development in harsh external environment? It should be easy to see that a 3-layer composite MEER geometry is necessary for corrosion resistance. So as you can see here, layer 1 is transparent and protect the reflector film on the top. And for layer 2, the key metric is reflection performance. And the layer 3 performs the dual role of structure support and corrosion protection. To develop this multi-layer MEER, several steps need to be done. First, we will focus on the material screening. Willow glass and aluminum and soda lime glass are selected as our optimal material, respectively. So let's take a look at their respective advantages. First, for layer 1, optical grade glass is necessary. The common commercially used is available solar reflector glasses are not suitable for us because they are heavy and bulky. So this limits throughput in mass manufacturing And an ultra thin glass called Willow Glass is the obvious candidate due to its lightweight flexibility. As you can see here, it shows a unique optical and magnetical properties enable us for faster roll-to-roll production. And the candidate for layer 2 is aluminum. The excellent optical reflectance and chemical stabilities make it an ideal candidate for reflective substance in large-scale infrastructures. And our calculations show that the recycled aluminum from Norway in a single year is sufficient to make enough mirror to cool the Earth back to the pre-industrial climates. And we would like to use the soda lime glass as layer 3. A soda lime glass is commonly used in daily life, and it's easy to get. Moreover, its low cost with the durable and chemical stable properties are also attractive. As you can see in this chart, its price is about $1 per square meter. And we are sure that with the production at the scale we need, the price can come down even more. And after the first step of material optimization, let's move on to explore manufacturing method and for large-scale mirror arrays. And data comparing several coating mirrors used in concentrated solar power applications are available. And this result shows that the spondering technology is preferred for this project. This is not only because the better reflectance achieved in the case of silver, but also because aluminum is not amenable to wet deposition. Considering the manufacturability and speed and scalability, a roll-to-roll process with a spondering deposition of aluminum coating on Willow glass is the preferred method to combine the layer 1 and the layer 2. And how does this manufacturing process work? Here is about the idealized roll-to-roll process flow. In this scheme, the roll-to-roll technique typically consists of several rollers, usually known as the web pass, and it winds the substrate material and through these rollers as it carry out a series of operations. And the technique applies additive subtractive steps onto the substrate as it moves along the web to create or produce a production or a product or part. And the final step is mirror fabrication. Is a hermetically attached top layer glass protector to the magnetically sturdy third layer. Laser welding system is a rising technology that has the potential at the stage of the prototyping. So ultra-fast laser welding has received significant attention due to its highly idealized localized heating, coupled with the ability to join optically transparent materials. And the manufacturing of integrated optical, magnetical, and electronic device often requires the join of the glass to glass or glass to the dissimilar materials, at the same time maintaining the glass surface conditions and the optical properties. And thank you for your attention. If you have any general or technical questions about any of the material covered, I'm happy to answer that. Thank you again.